Hello everyone and welcome to another video. In this video we'll be going over the first 15 problems from the F equals MA 2021 exam. And next video we'll be going over problem 16 to 25, so make sure to tune into the next video if you want to go over those problems. So with that out of the way, let's get started. Okay, so problem 1. We have a small ball that's released on a track with a rightwards velocity, and then the ball rolls without slipping. What that means is that there's no friction acting on the ball to slow it down. So the only force acting on the ball is gravity. So we have the ball starts at point A, turns around at point B, so it goes up the ramp and then goes back down and goes back to point A. And we want to find the graph that shows the speed of the ball as a function of time. So we should start off by actually drawing the graph and then seeing which of the following graphs is most similar to the graph that we drew. So we have t as our time axis and s as our y-axis. So important thing to note is that speed has to always be positive. It's unlike velocity, which can both be positive and negative. So our speed graph will always stay in the upper part. Okay. So let's start. When the ball initially starts rolling with rightwards velocity, it will keep having its velocity until it reaches this dip. Until it starts going up the ramp, it will have some constant rightwards velocity. So you have some straight constant speed. And then when it goes up the ramp to point B, its speed will start decreasing to 0 linearly. And this is because there will be a constant force of acceleration to slow it down. And we're using the kinematic formula V equals AT. We know that this is going to give us a linear graph. So it's just going to keep dropping until we reach B, where the speed is 0, and then it will come back down. So it's going to increase again, and then it's going to, after it reaches the bottom of the ramp, it will become constant again as we go back to A. So our graph will look like a V with two lines. So if we look at all of the following graphs that are the most similar, A, it does not work because it goes into the negative side. B does not work because it's curved. It has to be linear. C looks like the graph that we drew. So let's check the other ones as well. D, it doesn't work because it's negative, and neither does E because it's negative. So that means our answer must be C. For problem 2, we're using the same exact scenario where the ball rolls up, but this time we want the horizontal velocity as a function of time. So this time the velocity will be negative as well as being positive because it's velocity, not speed. So when the ball goes from point A to the point right here, it's going to be some constant positive velocity because it's moving to the right, and rightwards is positive. Then as it goes up the ramp, it starts decreasing. But this time we want the horizontal velocity. And when it goes up the ramp, the velocity component gets split into two parts, a horizontal part and a vertical part. So this means that it goes from a completely horizontal to having some horizontal and vertical. So the horizontal component will end up dropping a bit, and then it will start decreasing because it gets split into components. So we're going to have some drop, and then it's going to go down to 0 as it reaches B. And then it's just going to reflect across the x-axis because it's going to come down as negative. It's going to increase because now it's going from being a component to just being horizontal, and then it'll become constant again as it reaches from this bottom point to point A. So our graph will look something like this. So graph A is wrong because there's no drop. Graph B is also wrong because it has to be negative. C is wrong because it doesn't instantaneously become 0. Point D is also wrong because it doesn't stay 0 for a long portion of time. And this means that graph E is the correct one. Okay, so for problem 3, we have two rods that are both hinged to the ground at two different points. We have some left rod and a right rod. And on the left rod, we have a force of F being applied a distance of 2 meters away from the hinge. And on the right rod, we have a force of F prime being applied a distance 2 meters from the hinge. And we're told that the system is in equilibrium, and we want to find what force of F prime makes it so that the system is in equilibrium. And what this means when it's in equilibrium means that any point of the system must have a zero net force. So let's take the point right here where these two rods intersect or like touch each other. That means the net force at this point will have to equal zero in order for the rods to be in equilibrium. And we can find the net force on this in terms of F and F prime using torques. So we know that the torque along this rod, this left rod, is going to be constant. And torque is given as force times distance, or F times d. So we're given that the force is F and the distance is 2. So the torque is 2F. This means that at this point, the force applied by this the left rod onto the right rod is going to be 2F divided by the distance, which is 1. So the force that's being applied is 2F. And we can do the same thing on the right side. So we have 2F prime divided by 0.5 gives us the force applying the right rod on the left rod is a force of 4F prime. And in order for it to be in equilibrium, the 2F has to be equal to 4F prime. And this happens when F prime equals F over 2. Okay. Problem 4. We have two girls are standing side by side on the Earth's equator. One girl jumps up in her frame of reference to a small height h. So she's jumping to a height h and she lands a distance d away from another girl. So we have B and A. And if she jumps instead of a height of 2h, how far to the left of Bethany would she land? So we're trying to find out if she jumps to a height 2h, what is this new distance d? And the first thing we need to know is why is she moving to the west? Well, she's moving to the west because of the Coriolis force, which is a fictitious force, and the equation for this force is given as AC, or the Coriolis force, is equal to negative 2 times V cross omega, where omega is the angular velocity of the Earth and V is the velocity of the girl. So, and we can find the distance. So d, using the kinematic formula, d is equal to 1/2 at squared, because the initial velocity to the left is 0 since she's just jumping straight up vertically. So yeah, okay, so now let's try finding the time. The time that it takes for her to reach the ground again if she jumps to a height 2h compared to a height h will be time t equals t root 2. So you multiply the time by root 2 because the formula is d equals 1/2 gt squared. So if you're multiplying the height to 2d, then the time will have to become root 2t in order for the equation to hold. So this means that the total distance must be at least 2d. So we can cross out A, B, and C. But also, the acceleration of the girl due to Coriolis effect is going to be larger because the velocity at which she leaves the ground is larger, and the average velocity is also larger. So this means that it has to be larger than 2d. So that means we're left with E as our answer. Okay, for problem 5, we have a train that starts at city A and stops at city B. So we have a city A and a city B. And the distance between the two cities has a distance s. And we have the train's maximum acceleration is a1 and maximum deceleration is a2. What is the shortest time the train can travel between A and B? So the shortest time is when the train accelerates, and then as soon as the train accelerates, it starts decelerating. So at some point, let's say like this point right here, it will be accelerating at an acceleration of a1, and then it will immediately start decelerating at an acceleration of a2. So we want to find the time it will take for the train to travel the distance. So we can do this by solving a system of equations. So we know that at this point right here, when the train starts decelerating and accelerating, the velocity at this point must be the same. So A1 times T1, where T1 is the time it takes to accelerate, must be equal to T2 times A2, where T2 is the time it takes to decelerate. So we have T1 times A1 equals T2 times A2. And then for the distance, we know that the total distance must be equal to S. So distance is given as d is equal to 1/2 at squared. So this means that 1/2 a1 t1 squared plus 1/2 a2 t2 squared is equal to S. So now all we have to do is we just have to plug it in and solve the system of equations. So we have that we can use substitution because T1 is equal to T2 A2 over A1. And we can plug this value of T1 into the equation, so we get 1/2 A1 T2 squared A2 squared over T2, A1 squared. Okay, so I'll get back to you guys once I finish simplifying and solving for T2. Okay, so solving this equation gives us that T2 is equal to the square root of 2s over A2 squared over A1 plus A2. Okay, so this means that the total time, or T1 plus T2, is going to be equal to T2 times 1 plus A2 over A1. So this is going to be the total time. And if we plug this in and simplify, we get a really nice equation. We can also eliminate some options because we know we have a square root of 2. So anything with 2 outside of the square roots is wrong. So A, B, and E are all wrong. And then also, if you look at here, if we simplify this, we get 2s times A1 plus over A2 squared plus A2 times A1. And if you look in the answer choices, this is exactly D. But this is only giving us half of the time. We want the other half of the time when it's accelerating, not decelerating only. So D is also wrong. So that means our answer must be C. For problem 6, we have a cylindrical bucket of negligible mass, radius r and height h, open at the top, submerged in a density of rho, top height distance h from the surface. How much work is needed to pull the bucket slowly up so that its bottom is just above the lake surface? So we can use conservation of energy because the gravitational potential energy, GPE, is going to be equal to the work done by pulling plus the work done by the buoyant force. So we can find the gravitational potential energy change because the bottom is going from this point right here all the way up to this point, which is a distance of big H plus small h. So it's going to be mg, which is our weight, times the height difference, which is big H plus small h. And this is going to be equal to our work done by pulling plus our buoyant force. And Archimedes' principle tells us that the force done by the buoyant force is going to be equal to rho Vg, where rho is the density of the liquid, V is the volume of the object, and G is the gravitational acceleration. So we know that for a distance of h, the cylindrical bucket is going to be completely submerged in the water. So the work done by the buoyant force during this distance of big H is going to just be rho Vgh, where H is the volume of the bucket because the whole bucket is going to be under the water. But now, when the bucket from the top of the bucket is here to when the bottom of the bucket reaches the water line, the volume of the bucket will decrease. The amount of volume that's submerged will decrease. So this means we're going to add some rho gh, small h, times some volume. And this volume is going to be the average volume. And the average volume is going to be the total volume, the initial volume, which is V, minus the final volume, which is just 0, because when it's outside, none of the volume is submerged. All divided by 2 gives us our average volume, V average. Or this is just going to be V over 2. So our volume when it's going from the top of the surface to completely out is V over 2. And now we can solve for WP, or the work done by pulling. So if we expand the left-hand side, we get mgh plus mg lowercase h. And quickly, we know that m is going to be equal to rho v, density times the volume. So if we replace the mass with rho v, so get rid of all of this. So we replace it with rho vgh plus rho vgh. And we see that this term cancels out with this term, so we're only left with rho vgh on the left side is equal to the work done by pulling plus this term right here. And then we can subtract rho vgh over 2 from both sides, so we're left with that the work done by pulling is equal to rho vgh over 2. But we're not done yet because the volume is equal to pi r squared times h. So we need to plug this value of volume into the equation. And if we do that, we get that the work done by pulling is rho g pi r squared h squared over 2. So problem 7, we have a point mass that's sliding with speed v on a frictionless horizontal surface between two parallel walls that are initially a distance L apart. So we have two walls, distance of L, and a point mass is sliding with velocity v. It bounces off the walls perfectly elastically, and we're moving one of the walls a distance 0.01 L closer. So now the distance is going to be 0.99 L. And we're moving it with the speed of 0.0001 v. And we don't really care about the speed. It's not going to play a big role, but all that's telling us is that it's moving very slowly, which means that we can assume that it keeps bouncing elastically. So now this point mass is going to move with the new velocity vn. And the nice thing about bouncing elastically is that the distance traveled by the point mass is going to be constant, or in other words, this means that the velocity times this distance is going to be equal to this new velocity vn times the smaller distance 0.99 L. And if we solve for vn, we get 1.01 v. For problem 8, we have a mint produces 100,000 coins. Upon weighing some of them, we find that the coins vary slightly in weight with the independent uncertainty of 1%. We need to find how many coins must be randomly sampled and weighed so that the total uncertainty is 0.1%. And there's no other errors. So for this problem, we can just use the sum of error formula, which says that the total error, so sigma n, is equal to sigma 1 squared plus sigma 2 squared plus sigma 3 squared dot dot dot, where sigma 1, sigma 2, and sigma 3 are the uncertainties. So let's say that the mass, each coin has a mass m. Then the uncertainty in the masses is going to be 1% of m, which is 0.1 times m. So now this means that each of these sigmas must be 0.01 m. And let's say that there's n coins that need to be randomly sampled. And this means that we want the total weight of the coins, which is nm, to have an uncertainty of 0.1%. Or we want this total mass to be multiplied by 0.1%, which is 0.001. So we want the total uncertainty to be this right here. So if we plug in the values of sigma n and all of the other uncertainties, we get n times m times 0.001 is equal to the square root of 0.01 m squared plus 0.01 n squared, so on and so forth, n times, or n times 0.01 m squared. And if we can move this 0.01 m squared outside of the square root, so this gives us that nm times 0.01 is equal to 0.01 m square root of n. Now we see that the masses cancel, and we can just solve this equation for n. So if we multiply both sides by 100, we get n times 0.1 equals square root of n. And then if we square this, we get n squared times 0.01 equals n, or n is equal to 100. So our answer is D. For problem 9, we have NASA training astronauts to experience weightlessness with an airplane that flies in a parabolic arc with constant acceleration g towards the ground. So we have some plane is flying in a parabolic arc, and there is some acceleration g to the ground. And we want the astronauts to experience weightlessness. And we know that the plane is going to be on this trajectory for 25 seconds. And this is because of the change in altitude h. So the plane can only go a certain height h. Otherwise, it will probably escape the gravitational pull or something, or crash into the ground. But now NASA wants to simulate the gravitational acceleration of Mars, which is 3.7 meters per second squared. And we want to find what time can the plane simulate Mars's gravity. So now there's going to be a new parabola, probably looking like this, with the height h, but with the larger time. So the first thing we need to know is, how does it experience weightlessness? Well, the astronauts experience weightlessness when the normal force on their seats is equal to 0. So let's just draw the FBD of one of these people. So we have some guy that's on this parabolic arc, and they're experiencing weightlessness. So this means that the net force on the person, there's not going to be any normal force. The only force is their force of gravity, mg. So they're just going to be accelerating to the ground. So they're going to have an acceleration of g. But if you're trying to simulate Mars's gravity that has an acceleration of 3.7 meters per second squared, this means that you're going to have some normal force, n, is equal to 3.7 times your mass. And you're going to have your weight pointing downwards at mg. So this means that your net acceleration towards the ground is going to be g minus 3.17, which is 6.3, if we assume g is 10. So this is the acceleration of the plane now. Okay, so when it's experiencing weightlessness, the acceleration of the plane is 9.8 meters per second. But when it's trying to simulate Mars's gravity, it's going to be 6.3 meters per second. And suppose it was trying to simulate Earth's gravity, it would be 0 meters per second, because it would just have to stand straight, which is what we experience every single day because we're not accelerating. Now that we have these two accelerations, we know that the height that the plane travels, or h, is going to be some constant. It's going to be 1/2 at squared. So this means that a1 times t1 squared is going to be 1/2 times a2 times t2 squared. We can plug in our values of a1 as g, which is 10 meters per second, times 25 squared. This is going to be equal to our 6.3 meters per second times the new t squared. And solving for t gives us that t is 31 seconds. Let's go on to the next problem. Here we have a circular disc with mass m, so something like this, and it's on a flat frictionless horizontal table. The center of mass is right here, and it's at rest, and it's rotating with angular velocity omega naught. So mass m and omega naught. And then a stone is put at the edge right here, and it starts slowing down due to friction between the stone and the disc, and after some time they start rotating with the same angular frequency. So we have another stone of mass m, and after some time both of them rotate with some final frequency omega f. So this is a conservation of angular momentum problem. We know that the angular momentum about the center of mass is conserved in both instances. So initially, the angular momentum about the center of mass of the solid circular disc is 1/2 mr squared omega, where 1/2 mr squared is the moment of inertia of the disk, and this is equal to the final angular frequency times the moment of inertia of the system. So we know that the center of mass when the point mass is put is around r/2 from the center. So this distance is going to be r/2. So according to the parallel axis theorem, the moment of inertia of the disk at a distance r/2 from the center of mass is going to be 1/2 mr squared plus 1 m times r/2 squared, so r squared over 4. And then the moment of inertia of the point mass with respect to the center of mass is going to be plus m times the distance is r/2, so r squared over 4. And this thing inside the parentheses is the same thing as mr squared if we combine all the terms. And then we can cancel the mr squares on both sides. So we're left with the final angular frequency is equal to omega naught over 2, or c. Okay, so moving on, let's go to problem 11. We have 3 projectiles A, B, C are thrown off a cliff and take the trajectories as shown, A, B, and C. We want to rank the times that it takes to hit the ground. And again, this is just kinematics because the time that it takes to reach the ground is directly proportional to the height, because h is equal to 1/2 gt squared. So the higher up a projectile is thrown, the more time it will take for it to hit the ground. So we just need to rank them by increasing height. So the shortest time, which is the shortest height, is C. And this is going to be less than the second shortest time, or second shortest height, which is A. And then the largest height is B. So our time is going to be C is less than A is less than B. And if we look at our answer choices, we see that it's answer choice D. For problem 12, we have an object of mass m is equal to 1 kilogram is attached to a platform of mass m equals 4 kilograms with the spring of spring constant k equals 400 Newton meters. There is no friction here, but we have some friction between the platform and the ground, which is 0.1 coefficient of friction. And it's originally placed at an equilibrium position and given a horizontal velocity v. We want to find for what v will the platform never slip on the ground. So the platform will slip on the ground when the force exerted by the spring, this F right here, is going to be, it's greater than or equal to the force of static friction. And this maximum force done by the spring is when the spring is at its longest length. Let's try to find this force first. So we know this force is going to be equal to, well, the maximum static friction force is the normal force times the coefficient of friction, or mu. And in this case, our normal force is the smaller mass plus the bigger mass. So, or m plus big M times g times mu. So this gives us our maximum force. And we know this is also equal to kx, where x is the maximum distance. So this means that the maximum distance from equilibrium the mass travels is x is equal to m plus big M times g times mu all over k. Okay, and we can find this value of x using conservation of energy because there's no friction between the mass, the small mass, and the big mass. We know that 1/2 mv squared is the original energy of the mass spring system. And when the spring is fully extended, this is going to be, the velocity of the mass is going to be 0. And there's only going to be an potential spring force, which is 1/2 kx squared. And solving for x gives us that x is equal to v times the square root of m over k. So now we can plug this value of x into this equation above, and we can solve for v. So we get that v is equal to m plus big M times g times mu all over square root of m divided by k. So this means that if we plug in the values of m, big M, mu, and k, and g as 10 meters per second squared, we get that the velocity must be less than or equal to 0.25 meters per second squared. 0.25 meters per second. For the next problem, we have some cars driving along a track whose velocity vectors look like this. And we want to find its acceleration vector. In this problem, we're going to have two different sources of acceleration. We have our centripetal acceleration, AC, which is proportional to v squared. So the faster you move, the higher your centripetal acceleration vector will be. So if we draw it on each of these points, we have a small one for the first one, a bit bigger, even more bigger, and then very big on the last one. And all of these point towards the center of the circle because that's the direction that the centripetal acceleration always points towards. And we also have a tangential acceleration because the velocities are getting larger. And this tangential acceleration points and tangent to the track. So we're going to have some tangential acceleration like this, some tangential acceleration like this, and it's going to be approximately constant because it looks like the velocity is increasing by the same amount at each point. If we were to find the resultant vector, we would get some diagonal, and then we would get a larger diagonal but pointing a bit more towards the center, pointing a bit more, and then on the very last one, it will almost point towards the center, but not exactly, because we still have some tangential acceleration. So let's look at each of these graphs and see which one is the most similar. So for A, they forgot to account for centripetal acceleration, so that's wrong. For B, we only accounted for centripetal acceleration, and this doesn't even account for the fact that it's increasing since it's proportional to v squared, so B is wrong. C, this is the correct one for centripetal acceleration, but there is no tangential acceleration, so C is wrong. For D, we see that we have some centripetal acceleration and also some tangential acceleration, and it's increasing at each point. So that means D is the correct answer. And E, we see that although there is both tangential and centripetal, the centripetal acceleration is not increasing, it's staying constant. So E is wrong. So now on to problem 14. We have a bacterium cells, there's a drag force, F, which depends on the length of the cell, speed, and viscosity of the fluid, which has units of kilograms per meter seconds. And we're given that the cell has a length of 1 micrometer, swims at 20 micrometers per second. And we want to find the speed of a cell of length 0.5 micrometers. And we're given that all cells generate the same amount of force from their flagella. So the drag force F is going to be some constant C. And the viscosity is also going to stay constant. So the only thing that's changing is its length and the speed. So this is obviously a dimensional analysis question because we're given the force and what it's dependent on. So we know that the units of force are going to be kilograms, meters per second squared. The length of the cell R is going to be meters. V is meters per second, and the viscosity is going to be kilograms over meter seconds. And we see that we have a kilogram in the force and a kilogram in the viscosity, so this means that the force must be equal to viscosity times, so we have a meters per second on the left side, and we have 1 over meter seconds on the right side. If we multiply this by velocity, which is meters per second, we see we have our seconds squared. So multiply this by velocity gives us 1 over seconds squared. And we're trying to get to meters per second squared. And we can do this by multiplying by r. So if we multiply by r, we now get a meters on the top. So our units are now balanced on both sides. So this means that the force is equal to our viscosity times the speed times the length of the cell. And we also know that the force and the viscosity are constant. So this means that the velocity of the cell times the radius of the cell must be constant. So this must be some constant c. Therefore, V1 times R1 must be equal to V2 times R2. And we're given that V1 is 20 and R1 is 1. So we have 20 equals V2, which we're trying to solve for, and R1, which is 0.5. So V2 times 0.5. And if we solve for V2, we get it's 40 micrometers per second. Okay, so for the last question, we have a block is released from rest at the top of a frictionless ramp with horizontal length L and inclination theta. And we're given that L is constant, and we want to find what value of theta minimizes the time needed for the block to reach the bottom of the ramp. For this problem, we can use kinematic equations as well. If we use the formula, d is equal to 1/2 at squared, and we can try minimizing the t. We know that the distance the block travels is going to be L over cosine theta. So this is our d. And the acceleration of the block parallel to the ramp, this acceleration right here, it can be found by splitting up the weight. So we have mg is split up into two components, a parallel component and a perpendicular component. And the parallel component is going to be mg sine theta. So this is our a. So if we plug our values of d and a back into the equation, we get L over cosine theta equals 1/2 times mg sine theta equals times t squared. So if we solve for t, we get t is equal to the square root of 2L over mg sine theta cosine theta. We want to find what value of theta minimizes the time for the block to reach the bottom of the ramp. So if we want to decrease t, we want to increase the denominator, because increasing the denominator will decrease the time. So we want to find the maximum value of mg sine theta cosine theta. And mg are fixed, so we already know the values of m and g. So we just need to find the maximum value of sine theta times cosine theta. We want to see what value of theta maximizes this. So there's two ways you can do this. You can just plug in the answer choices into this sine theta cosine theta and see which one is the largest. And if you do this, you get 45 degrees. But if you know calculus, you can do this a faster way by taking the derivative of this with respect to theta. So if we take the derivative of this with respect to theta and set this equal to 0, we can actually solve for theta. We use the product rule, and we get d sine theta with respect to theta times cosine theta. So sine theta, the derivative of sine theta with respect to theta is cosine theta. So cosine theta times cosine theta is cosine squared theta plus sine theta times the derivative of cosine theta with respect to theta, which is negative sine theta, and this is equal to 0. So this means that cosine squared theta is equal to sine squared theta, or cosine theta is equal to sine theta. And this happens when theta is 45 degrees, because cosine of 45 degrees is root 2 over 2, and sine of 45 degrees is root 2 over 2. So our answer is B, 45 degrees. Okay, thank you guys for watching, and remember to tune in the next video if you want the solutions to problem 16 to 25. Thank you guys for watching, and I'll see you guys later.